You know, when you or I open our eyes in the morning, there's absolutely zero conscious effort involved.
Right. Yeah.
I
None of
mean,
it's
look
that.
across the room, and your brain just instantly registers things. Like, that's a window, that's a chair, and, that's the alarm clock I really want to throw across the room.
Exactly.
It is instantaneous, it's effortless, and entirely natural. But if you try to teach a computer to do that exact same thing,
Oh, historically, you might as well have been asking a toaster to write a symphony.
exactly. It was basically impossible. I mean, for decades, a computer looking at a digital photograph didn't see a chair or a window. It just saw this massive, totally meaningless grid of numbers representing pixel colors.
Yeah, the context, the meaning, the actual quote-unquote seeing was completely absent. It was an incredibly steep uphill battle. The early attempts required manually programming, like edge detection, color thresholding, and all these rigid geometric rules.
Right.
And if the lighting changed even a little or, the chair was turned sideways, the entire system just broke down.
Which brings us to what we're doing today. We are taking a shortcut through the technical manuals to bring you the most critical insights from the bleeding edge of AI. We've got our hands on a deep dive into a Microsoft Learn module covering computer vision capabilities in Azure Foundry.
It's a fascinating module.
It really is. And our mission for you today isn't just to look at how AI models are interpreting the visual world, but how they're literally creating it. Because, we are not talking about parlor tricks or generating funny memes here.
No, not at all.
The stakes outlined in this source material are intensely practical. I mean, AI vision systems are currently monitoring retail store shelves, instantly detecting when products are out of stock or misplaced so they can update inventory in real time.
And it scales far beyond retail, too. Manufacturing assembly lines use these models to spot microscopic surface defects on parts as they just, whiz by on the belt, which drastically reduces waste. Yeah, and they're analyzing medical x-rays and MRI scans to highlight anomalies, like finding early-stage tumors. And of course, they're acting as the literal eyes for autonomous vehicles.
Right, reading the road.
Exactly. Identifying pedestrians, lane markings, and road signs in dynamic, fast-moving environments. This technology has basically become a core operational infrastructure for safety and logistics.
Okay, let's unpack this, because to understand how an AI can do all of that, we have to look at the underlying engine. The source material centers on this massive paradigm shift toward what they call multimodal models.
Yes, that's the key term here.
Because before an AI can create or predict anything, it has to fundamentally understand it. And in the olden days, if you wanted an AI to understand an image, you built this rigid vision pipeline.
Right, the lossy pipeline.
Yeah, exactly. You sent a photo to an object detector, it spit back a list of text tags like dog, grass, frisbee, and then you fed those text tags into a completely separate language model to try and guess what was actually happening in the scene.
Which is an inherently lossy process. You lose all the nuance, the spatial relationships, the lighting, the mood,
Yeah,
everything.
yeah.
But a multimodal model, like the vision-enabled GPTs available in Microsoft Foundry, just eliminates that translation layer entirely. Multimodal essentially means the model architecture is designed from the ground up to process multiple kinds of data natively.
That's not translating.
No, it handles text, images, audio, and video, all within the exact same multidimensional latent space.
Right, so instead of having an object detector translate pixels into words for a text model, the AI encodes the pixels and the text into the exact same mathematical vocabulary. It's basically like giving an AI brain a pair of eyes directly.
That's a great way to put it. That native integration is what allows for true visual reasoning.
Yeah.
You hand the image directly to the vision-enabled GPT model and ask it a question in plain English.
And it just gets it.
Yeah, because the visual data and the text prompt are processed together, the model understands the context. It doesn't just see a dog and a frisbee. It understands that the dog is midair, actively intercepting the frisbee.
I do want to push back on the mechanics of that, though. If I'm a developer writing a Python script to build one of these retail inventory applications, how does the code physically see the image? I mean, I can't just hold a photograph up to my server. How does the image data physically get into the AI's multidimensional space alongside my text prompt?
Well, if you're building an application in code, you're likely using the Azure OpenAI Python SDK. So you point the library to your Foundry endpoint, and then you construct your payload.
Okay.
A single API request contains both your text instruction like what objects are visible in this image and the image data itself.
Yeah.
The API allows you to provide that image in one of two ways.
Which are?
You can provide a URL pointing to a publicly accessible image, or you can send the raw image data directly inside the payload as a base64 encoded string.
Okay, the documentation actually shows some incredible examples of this payload in action. Like, in one screenshot, they feed an image of a giraffe standing on a savanna into the GPT 4.1 mini model.
Right, the giraffe example.
Yeah, and the AI doesn't just output giraffe, it provides this highly structural description. It points out the long neck, the irregular brown patches, the horn-like structures on its head, which it calls ossicones, apparently.
Yeah, it's very detailed.
And it deduces the savanna habitat based on the background vegetation. There's another example, too, where a Python terminal runs a script, passes an image file, asks, "What's the animal in this image?" And the terminal just calmly prints back, "The animal in the image is an elephant."
If we connect this to the bigger picture, the models you're referencing represent specific tiers of capability within Microsoft Foundry. The model catalog gives you architectural options based on your compute budget and latency requirements.
Makes sense.
So the GPT 4.1 series, which ranges from nano to mini, those are your general-purpose multimodal workhorses. They're highly optimized for things like image description, visual question answering, or interpreting charts.
Right.
But for heavy enterprise workloads, there's the GPT-5 series, like GPT 5.1 and 5.2.
And the source material describes those as designed for complex agentic scenarios, right? Meaning the AI isn't just passively describing a photo, it's acting as an independent agent making actual operational decisions.
Exactly. The GPT-5 models can handle massive, complex contexts and output the highly structured data required for tool calling.
Oh, wow.
Yeah, so if an AI agent monitoring a server room via camera sees a specific red error light on a server rack, it doesn't just, log a description of the light. An agentic model has the reasoning capability to recognize the error, query an external database for the troubleshooting protocol, and automatically execute a reboot script.
That is wild.
It performs complex visual reasoning as part of an automated workflow.
Here's where it gets really interesting. If these models are mapping pixels and text to the same mathematical space to translate an image of an elephant into the word elephant, they can throw the process into reverse, right?
Yeah.
We can feed them text and have them translate that into pixels.
Exactly. Text-to-image inferencing is a massive component of Microsoft Foundry. It relies on diffusion models, which operate by taking a field of random visual noise and iteratively refining it step by step until it matches the text description you provided in the prompt.
So the source module highlights the GPT Image 1 family for this, but it breaks it down into different versions. It seems like selecting the right model is kind of a balancing act between the number of diffusion steps, which dictates the quality and the cost of the compute.
Yeah, that's exactly right.
Yeah.
For most new enterprise projects, Microsoft points developers toward the GPT Image 1.5 model. It's designed for high-fidelity image creation, precise image-to-image transformations, and localized editing. It uses a higher step count in the diffusion process, which requires more compute, but it yields the visual accuracy required for, branding, marketing, and professional design workflows.
Right. And then you have GPT Image 1, which is the general purpose model built on the earlier DELI architecture, good for creative prototyping.
Exactly.
But if you're building an application that needs to generate thousands of images a minute, you would drop down to GPT Image 1 Mini. You sacrifice a tiny bit of maximum visual fidelity because it uses fewer diffusion steps, but you get drastically lower latency and reduced compute costs. It's built for those high-volume automated jobs.
And the Foundry platform also supports third-party open-source models, which is important. The module specifically highlights the FLUX family created by Black Forest Labs.
Oh, right.
Yeah, FLUX models are renowned for their highly photorealistic outputs and stylistic flexibility, and giving developers the option to route requests to either proprietary Microsoft models or open-source models prevents vendor lock-in.
That's a huge deal for enterprises. But regardless of whether you use GPT Image 1.5 or FLUX, developers run into a very specific technical hurdle when receiving these generated images back into their application. We touched on base64 encoding earlier, but I want to look at why it is absolutely mandatory here.
Yeah, it's a critical concept.
I have an analogy for this, actually. So when your Python script asks the API to generate an image, it communicates using JSON payloads. And JSON is strictly a text-only format.
Right.
But a generated image is raw binary data. if the API tries to shove raw binary bytes into a text-only JSON response, it completely corrupts the data structure. It's like trying to shove a wet oil painting into a standard paper envelope.
Oh, that's a perfect analogy.
Right. It ruins the envelope and it destroys the painting.
Exactly. The communication protocols of the web are fundamentally designed to transmit text characters, not raw binary media.
Right. So base64 encoding acts as this like universal translator. It takes that wet oil painting, the binary data, and maps those 8-bit binary numbers into 6-bit safe ASCII text characters. It essentially turns the image into a massive alphabet soup string of standard text.
Yep.
And the JSON envelope can safely carry that string of text back to your Python script. Then your script simply decodes the alphabet soup back into binary and saves it as a crisp PNG or JPEG file.
And the underlying math of mapping those bits allows raw binary files to hitch a ride inside standard text payloads without corrupting the JSON parsing. Understanding that mechanism is a core requirement for building these systems.
Right.
I mean, media and publishing companies are using this exact pipeline to move away from static stock photo libraries. They build dynamic, automated visual content creation directly into their CMS, generating bespoke, high-quality images on the fly based on real-time news data.
So we figured out how to generate a static world in a single frame. But the real world is governed by time. The next logical step to explore is how the AI handles temporal consistency to generate video.
And moving from a single image to a video requires a monumental leap in computational power. Generating a single frame is one thing. Generating 60 frames per second, where the lighting, the physics, and object geometry remain mathematically consistent from one frame to the next without flickering or morphing, that is an incredibly complex problem.
I can imagine.
In Microsoft Foundry, this temporal generation is handled by the Sora models.
And the source breaks down two native versions of that. There is Sora 1, the foundational text-to-video model. It takes a text or image prompt and generates a short clip, but then the module dives into Sora 2, which is currently in public preview.
Yeah.
It introduces audio generation directly into the video output, but the feature that really stands out the most is its video-to-video remixing capability.
What's fascinating here is that video-to-video remixing solves a massive problem in AI video generation. In earlier models like Sora 1, the diffusion process starts from random noise. So if you generate a video of a city street and you like the motion, but you want to change the color of a specific car in the background, you have to tweak your text prompt and regenerate the whole thing.
Right.
And because the model starts from a new seed of random noise, the new video will have a completely different camera angle, different lighting, and different pedestrian movements. You lose the entire underlying structure.
Ah, so remixing anchors the latent space.
Precisely. With Sora 2's remixing, you input an existing video. The model uses the temporal and structural data of that source video as the foundational noise constraint.
Oh, wow.
Yeah. It allows you to make targeted, localized edits like just changing the car color, while maintaining the exact physics, camera movement, and geometry of the original clip. It turns the model from a random generation engine into a precise cinematic editing tool.
Because these models are generating hyper-realistic footage, the source documentation dedicates a lot of space to the responsible AI guardrails enforced at the platform level. Foundry places strict API-level limits on generating real people, blocks copyrighted characters, and filters restricted content.
Right, which is absolutely necessary. Enterprise deployments require those hard guardrails to prevent corporate tools from being used to generate deepfakes or copyright-infringing material.
Exactly.
The platform architecture will simply reject the payload before the compute process even begins if it detects a violation.
Now, as I was reading through the section on Sora, I noticed a massive technical shift in how we are instructed to communicate with the API.
Yes.
Because for image analysis and image generation, the module uses the Azure OpenAI Python SDK. It's clean, synchronous, and takes just a few lines of code. But the moment we get to video generation, the documentation completely drops the SDK. It suddenly pivots to discussing the REST interface and using a command line tool called curl. If I'm a developer, I'm wondering why my nice, clean Python library has been replaced by raw command line requests.
It comes down to the fundamental nature of HTTP requests and the sheer compute time required for video. When you ask an AI to describe an image of a giraffe, the model processes the request in, maybe 2 or 3 seconds.
Right.
A standard HTTP connection can easily stay open for 3 seconds while waiting for the server's response. This is a synchronous connection.
But standard web connections are stateless, and they have strict timeouts. If I leave a connection open waiting for a response, it's going to time out and sever the connection after, what, 30 or 60 seconds?
Exactly.
And according to the text, a Sora video can take anywhere from 1 to 5 minutes to render. So if I try a synchronous connection, my application will literally crash while the video is still rendering.
A synchronous call is mathematically impossible here. You must use an asynchronous architecture. You aren't staying on the line waiting for the video. You are dropping off a work order and checking back later.
Okay.
The module outlines a mandatory 3-step dance for managing this asynchronous REST API process.
Right, so step 1 has to be creating the job. I send my text prompt, my resolution, and my length parameters to the server. But instead of sending a video back, the server sends me a 202 accepted status and a tiny text receipt, a videoid.
Yep. And once you have that videoid, you move to step 2, which is the polling loop. Your application takes that ID and periodically pings the server's status endpoint. You're essentially asking the server, is job 123 completed, running, or failed?
Right.
And you might program your app to check every 10 or 20 seconds.
And finally, step 3. Once the polling loop receives a completed status, I make one final HTTP request to a specific URL to actually download the finished MP4 file. And this totally explains why the documentation introduces curl. Because curl isn't just a generic tool, it is the foundational way to send raw, stateless HTTP requests from a command line.
Right. And SDK is just a developer-friendly wrapper that hides all of those HTTP headers and polling loops from you.
Yeah.
But for cutting-edge preview features like Sora 2 or complex asynchronous workflows, an SDK might not be fully updated, or it might obscure the control you really need over the polling intervals. Understanding how to use curl to manually construct raw REST API requests, manage authorization headers, and handle JSON payloads, it means you understand the actual circulatory system of the platform. You aren't dependent on a wrapper.
So what does this all mean? We've covered a massive amount of ground today. We started by looking at how visual AI is actively running the world, from cameras managing retail inventory to systems inspecting manufacturing lines. We saw that multimodal models like the GPT 4.1 and GPT 5 series eliminate the lossy translation layer between vision and text. They map pixels and words into the same multidimensional space, allowing an AI to truly understand a scene or autonomously execute a server reboot based on a visual error light.
And we explored the reverse engineering of that latent space, detailing how diffusion models like GPT Image 1.5 and FLUX generate pixels from text. We broke down the critical mechanism of base64 encoding, allowing raw binary images to travel safely inside text-only JSON payloads.
Right.
And finally, we examined the complexities of temporal consistency with Sora 2, learning that the sheer compute time of video generation requires a fundamental architectural shift from synchronous SDK calls to asynchronous REST API polling loops.
For you listening, this is where the theoretical becomes highly practical. Knowing that Sora 2 can generate video is interesting, but knowing why your architecture must utilize an asynchronous polling loop to handle the stateless timeouts of a 5-minute render, that is what gives you a competitive edge. That is what separates someone who just reads about AI from someone who can actually design, build, and deploy resilient enterprise systems.
The underlying mechanics dictate the possibilities. When you understand the infrastructure, you can begin to manipulate it.
Exactly. And before we wrap up, I want to leave you with a final thought to mull over. A little something looking out toward the horizon. We know from the source material that Sora 2 can already perform precise video-to-video remixing, locking the temporal structure of a video to make targeted, localized edits.
Right.
And we know from the GPT-5 section that AI agents are becoming increasingly autonomous, capable of complex reasoning and tool execution in real time. If we combine those two trajectories, how long until we aren't just generating static MP4s that we download and watch passively?
Oh, that's a fascinating thought.
Right. How long until these multimodal agents are generating entirely interactive, real-time visual worlds? Worlds that adapt, remix, and render themselves live based on our spoken commands and physical movements as we walk through them.
The gap between a machine simply mapping pixels to text and actively, temporally hallucinating a reactive reality is closing at an astonishing rate.
It really is. Remember where we started today. Human vision is effortless. We just open our eyes and the world is there. We are rapidly approaching a point where machines won't just effortlessly see our world. They will effortlessly generate entirely new ones in real time. Thanks for joining us on this deep dive. Keep questioning, keep exploring, and we'll see you next time.